The chemical elements. An element is a pure substance consisting of atoms that have the same number of protons. For example, all hydrogen atoms have 1 proton. All helium atoms have 2, lithium 3, etc. And that's how the elements are arranged on the periodic table. There are 92 chemical elements that occur naturally, hydrogen through uranium. Now, the way that the periodic table is arranged is a little confusing, like why are these 2 rows down here pulled out? I will take a look at that in the next slide. Elements beyond uranium are called the transuranium elements, so trans meaning beyond, so the elements beyond uranium are synthetic and will undergo radioactive decay. So the code that's being used here, the key, is green are naturally occurring, and then the purple are synthetic. So you can see everything after uranium is synthetic. And I'm pointing to these down here because those actually are the first ones, not these here, as you'll see in the next slide. So this is our periodic table, the way it's typically arranged, but you can see that you have these arrows down here. These 2 rows are actually pulled out. They belong right here. So this uranium is here, so uranium is down here, and then after we get to the end here, then we pick up here. And so you can see that that arrangement is laid out in linear fashion down below here. Now, this arrangement on the periodic table and why those 2 rows are pulled out and all of that, we'll talk about in our next unit. Just pointing it out to you now. All the elements up to uranium are naturally occurring, and then beyond uranium are synthetic, artificially made. They have very short lives. We'll talk about that later on. Atoms are the smallest unit of an element and contain the same number of electrons and protons. So let's take carbon as an example. Carbon is atomic number 6, so it has 6 protons, and unless you're told otherwise, and if it's referred to as an atom, it's neutrally charged, has no charge, so it must mean it has the same number of electrons. Whereas ions are atoms that have lost or gained electrons. So there's 2 types of ions that have positive charge and ions that have negative charges. Positive ions are called cations. It's pronounced with a hard C, cations. Electrons have been lost. Remember that protons are positively charged, electrons are negatively charged. So if you lose electrons, you have more protons than electrons, so it's going to be positively charged. So let's again use carbon as an example here. So in this example, carbon has a positive 4 charge. So it has the 6 protons. Remember, that defines carbon. We can't change the number of protons or it would be a different element. But we can change the number of electrons. So in this case, we've lost 4 electrons. So it now has a positive 4 charge. And once again, remember that when we write the chemical symbol with a charge, if it has a charge, the sign goes after the number, Now, if it has more electrons than protons, it's called an anion. It's negatively charged. And so again, let's look at carbon as an example. In this case, carbon has gained 4 electrons. So rather than the 6 electrons the neutral atom has, it now has 10 electrons. So it has a negative 4 charge. The simplest way to think of it is it has 4 more electrons than protons. So it has a negative 4 charge. So let me kind of recap here, because there's 3 different species of elements that we'll be looking at. Atoms are just the basic representation of an element. What is an element? If you had a sample of gold, say, well, it's made up of gold atoms that all have the same number of protons and electrons. But if we have lost or gained electrons, then it's referred to as an ion. If it lost electrons, it's a cation. If it gained electrons, it's an anion. Okay, then we have isotopes, and this is where we look at atoms with different number of neutrons. So isotopes are atoms of the same element with different number of neutrons. So let's look at this as an example, and this is potassium. So you can see for each one of these, and what this is a blow up of the nucleus of the atom. So the fuzzy area here, that's called an electron cloud. We'll talk about later on in the unit. And you see that you have 19 electrons within that electron cloud, and deep, deep, deep inside we have the nucleus of the atom. They're incredibly small. It's been blown up, and you can see that in this nucleus we have 19 protons and 20 neutrons. Here we have 19 protons and 21 neutrons. Here, 19 protons and 22 neutrons. So again, they're all potassium because they all have the same number of neutrons. Same number of protons, but they have a different number of neutrons. Now, when we talk about isotopes, we pretty much just ignore the electron. So we're not concerned. You're not going to have a case where it's both an ion and an isotope. Now, it can be, but you're not going to be asked about that. It'll either be ions we're talking about, where the only difference is the number of electrons, or we'll be talking about isotopes where the only difference will be the number of neutrons. And by the way, you may have noticed that this little diagram here uses that convention I mentioned in our last notes. Sometimes you'll see the symbol for proton with a little positive sign on it, and for neutrons you'll see a little 0 on it. We don't use that, but that's what it means. Okay, now we have different ways of representing isotopes, and these are the symbolic notations that we can use. There's 3 different ones. Now, you've already seen this first one. This is our symbolic notation, or using the chemical symbol of the element, which would be a capital K, and then the 19 is the atomic number, and the 39 is the mass number. But we can also write it like this, where we write out the entire name of the element, and then hyphen mass number. And so the 39 here, remember, is the mass number, the total number of protons plus neutrons, the mass number. Well, that's what that number is there. A lot of times students mistake that to be the number of neutrons. So no, there is no, in none of this, there is no number that you look at to give you the number of neutrons. You always have to figure it out by subtracting the atomic number from the mass number. Now, we don't include 19 here because we really don't need it if you think about it. If 19 defines the element, well, then why do we need to say 19? If it's potassium, then it's a given. It has 19 protons. Now, we can also write it in a more simpler manner, just using the symbol hyphen 39. So all 3 of these would be a way that we can represent this particular isotope. And as you might guess, we could do exactly the same for this isotope and this isotope, where the only difference will be the mass number. So this is called potassium 40, and this is potassium 41. The only difference between the 3 are the number of neutrons, which means that we have a different mass number. Okay. The 4 fundamental forces of nature. Okay, so we have a little table here we're going to fill out. The 4 forces are gravity, electrostatic, strong nuclear force, and weak nuclear force. Now, what affects gravity, or what is affected by gravity, is mass. If anything that has mass, the pencil that you may be holding, the chair that you're sitting on, anything that has mass is attracted to one another. Of course, you have mass, the Earth has mass, so when you jump up and down, it's because the Earth's gravitational force is pulling on you. But, believe it or not, your mass is also pulling on the Earth. Electrostatic is anything that has a charged particle. So in its simplest form, it would be a proton or an electron, but we can have cations and anions that are charged particles as well. And now for it, it's either an attractive force or a repulsive force. And you probably already know this, but if you have opposite charges, positive, negative, they attract one another. And you may have heard that expression, opposites attract, and that's where it comes from. But if they're like charges, then they repel one another. And so the arrows here are representing that they're moving away from each other. They want nothing to do with each other. They're like charges. So gravity is only attraction. Electrostatic is either attraction or repulsion, depending upon the charges. And then for the strong nuclear force, it only affects nucleons. Remember, nucleons are protons and neutrons. It's attraction only, and it's a very, very short range. And then the weak nuclear force has to deal with nuclear decay, not something that we're going to get into, but it's why atoms will sometimes spontaneously break apart into radioactive nuclear decay. Okay, now let's look at the relative strength. Most people think that gravity is the strongest of them all. So let's see if that's true. We will assign the electrostatic force 1. Remember, relative means one thing just compared to another. So if the electrostatic force is 1, what do you think? How would gravity compare? And so usually I Q&A with my class, but I'll have to give you a second to try to guess yourself, and then I'll tell you the answer. The answer is it's much smaller. It is much, much, much smaller than you would ever imagine. It's 10 to the negative 40. Of all the forces, it is by far the weakest. Now, of course, we think of it as being super strong because we are super tiny little creatures on a very, very, comparatively very, very large planet. But if we were to look at the 4 forces, it is the weakest by far. And then the strong nuclear force is about 100 times greater than the electrostatic force. Okay. Now, the strong nuclear force explains why protons can be next to one another within a nucleus. Remember that protons are positively charged. So if you ever stop to think about it, why would they be next to each other inside the nucleus? Well, it's because when they come so close to one another, the strong nuclear force kicks in, and they have to be almost virtually touching one another. The strong nuclear force will kick in, which is 100 times greater than the force of repulsion that they would experience due to the electrostatic force. So that's why protons can exist within the nucleus. And then the weak nuclear force is about 10 to the negative 10. Now, the weak nuclear force of all of these, this is the one that's hardest to understand. If you want to kill a weekend sometime, go on Wikipedia and read everything they have to say about the weak nuclear force. And what you'll see over and over is that it's not fully understood. Okay, so I'll leave that for you to research on your own. But these, up to the electrostatic force and the strong nuclear force, this explains atoms. This is what we are mostly interested in. The band of stability. All right, now this little diagram here, I would encourage you to try to copy this diagram down in a very simplistic manner. You don't need to draw in any detail. But what it represents, it's the number of neutrons plotted against the number of protons. And so as you go across the x-axis here, you're simply going across the periodic table, going across and down as the atomic numbers increase. So hydrogen is atomic number 1, helium is atomic number 2, lithium is atomic number 3, calcium is atomic number 20, on and on. Well, if you had an equal number of protons and neutrons, well, then the line would be right here. And that's what this line represents, an equal number of protons and neutrons. But we find as we have more and more protons in the nucleus, because the protons repel one another, we need more and more neutrons in order for the atom's nucleus to remain stable. And so this is called the band of stability, where we have more neutrons than protons in order for the nucleus to be stable. Okay. The stability of the nucleus is dependent on the strong nuclear force being sufficient to overcome all proton-proton repulsions. Okay, so it's the nucleus, many protons inside there. So you can kind of think of the neutron as being the glue to help hold everything together. When atoms contain too many protons, additional neutrons are needed to have a stable nuclei. It's called the band of stability, where you have more neutrons than protons in order for an element's nucleus to be stable. Atomic mass. When we look on the periodic table, we have the chemical symbol of the element, the atomic number. Remember, that is the number of protons. But then we have this other number that has decimal places. And that's the one that students will often mistake for mass number. That is not the mass number. We haven't talked about it yet. We are now just talking about it. It's called atomic mass. So what we need to do in the remaining notes here is figure out, how do we calculate that number, and what does that number come from? Recall that the mass of one proton is almost exactly equal to the mass of a neutron. In your last notes, you were given these two numbers as the actual mass of a proton and a neutron, and you can see they're not exactly equal to one another. Pretty close, but not exactly. Okay. Scientists have defined a unit that is the average mass of these two nucleons, and it's called the atomic mass unit, AMU. In recent years, it's been abbreviated to just U, but we're still going to be using AMU. So AMUs are atomic mass units. So it's the average mass between the two. Now, there's a little bit of a problem. Protons and neutrons are way too small to measure individually. So we have to look at atoms that are readily available that we can use to determine what that mass would be. Where one atomic mass at one AMU is equal to 1/12. Let me start over. Where one atomic mass unit is equal to 1/12 the mass of the carbon-12 isotope. So this is a definition you want to lock away. It's a very important definition. Now in your notes, make sure you're clear. It's 1/12. And I say that because quite often students will give as the answer to a question regarding this 1/2. And I think they just can't read their own writing. It's 1/12. Now carbon-12, if we were to look at the atom itself, remember that that means that it has 6 protons and 6 neutrons. So it's a real convenient element to use. It's readily available. Almost all carbon is carbon-12, and it has exactly the same number of protons as neutrons. So if we take the mass of carbon-12 and simply divide it by 12, we would have 1 AMU, or another way of saying it is we would have the average mass of a proton and a neutron. Okay. All atomic masses are now based on this definition. Little side note here, you don't need to copy it down, but it's kind of interesting. In 1961, carbon-12 became the official isotope to use. Before this, oxygen-16 was used, where 1 AMU is equal to 1/16 the mass of the oxygen-16 isotope. Now, oxygen-16, like carbon-12, has the same number of protons and neutrons. Oxygen is atomic number 8, so oxygen-16 would mean that it has 8 protons and 8 neutrons. But oxygen is a little difficult to deal with, mainly because it's a gas, whereas carbon is a solid. So we moved over to carbon in 1961. All right, now, how is atomic mass calculated? How do we come up with that number? So break out your calculator and your periodic table. So when we look at this number, 39.10, well, remember that potassium has 3 different isotopes. So what do? Add the 3 together and divide by 3 to get that number? Well, the problem with that is that some isotopes are really rare and others are much more abundant. So when we do this, we have to consider the fact that some are much more abundant than others. So what we use is what's called a weighted average. Atomic mass is a weighted average calculation. Okay, now this is the general formula for a weighted average calculation. I'm not sure if you're familiar with the symbol. It's sigma. It's used to mean sum or to add up. And so this is representing adding up all the percentages of something times all the amount of whatever it is you're measuring. We're going to do some examples here, so don't fret. Now, this can better be represented, maybe more easily understood, like this. So you have a certain percentage of something times a certain amount plus another percentage of the same thing times an amount, etc. So let's say that we had 3 different measurements that we were making, say, of height. Let's say that this one was 20% and this one was 10%. Well, then this would have to be 70%. So the percentages add together to give us 100. Okay, let's do an example that you might be able to relate to. What would be a student's weighted average grade based on the following scores? Okay, now you know that this class grades are weighted 80% tests and quizzes and 20% everything else. We'll call that homework. So let's say that a student had, of 700 points possible for tests, had 582 points. And for all the points possible for homework, had 184 out of 200. So what we would do, we would use this formula up here. We would have percent times this amount plus percent times this amount. Okay, so Now, when we multiply by percentages, I hope you already know, but if you don't, we must convert it to a decimal. So percentages must be converted to decimals. Move the decimal place, the decimal 2 places to the left. So if the number was 5.44%, we need to move that decimal place 2 places over to the left. So before we plug it into a calculation, we would rewrite it 0.0544. All right, so this calculation here, first I want 80% times this ratio. So I've converted the 80% to 0.800. Now, something's coming down the pike here later on in this course called significant figures. We're not going to talk about that now, but notice that this has a decimal point 0. Now in math you would ignore that, but in science you never ignore that. So when I move the decimal place over 2 places to the left, I still keep those zeros, and so you see those there. So I'm going to multiply this ratio, 582 over 700 times 0.8. But then, looking at our general formula here, I'll add to it the next, which is 20% I've converted to 0.200 times this ratio. Now, when you plug this into your calculator, you would get 0.849. Now, we want a percentage, so this is our decimal percentage. So to convert it back, going in the opposite direction to make it a percent, this would be 84.9%, moving the decimal place over to the right 2 places. All right. Now, we're going to do an actual example here for an isotope. So if you'd like to try to do this calculation yourself, you're welcome to. If you were to plug this into your calculator, the way that you would want to do it is using the parentheses, 0.8 times parentheses, 5 or times, actually you wouldn't need parentheses, what I'm saying. Just 0.8 times 582 divided by 700 plus 0.2 times 184 divided by 200 equals. And you should get this. Okay, now atomic mass, the percentage is the percent abundance that we would find it in nature times the mass. So let's look at an actual example. Use the data below to calculate the atomic mass for magnesium. So you can see you have 3 different isotopes and a different abundance for each one. Now what this means is if you had a sample of magnesium, and it wouldn't matter where you got it from, it's just kind of universal. If you had a sample of magnesium, 78.7% would be magnesium 24, 10.13% would be magnesium 25, and 11.17% would be magnesium 26. Now, the actual masses of each one of these, based upon the definition we talked about earlier for an atomic mass unit, would be these numbers here. So we have everything that we need to calculate the atomic mass for potassium. Now, remember, the mass here is not for magnesium, is not the atomic mass for magnesium, it's the atomic mass for magnesium 24 and then 25, 26 respectively. So in order to calculate the atomic mass for magnesium, we need to use the formula up here. Okay, so it'll look like this. So I'm converting the 78.7% into a decimal, moving the decimal place over 2 places to the left, times the mass, which is 23.99. And then I'll add to that the 10.13% that I've converted into a decimal times its mass, plus the 11.17% I've converted into a decimal times its mass. Okay, now what I'm going to encourage you to do is to stop the, let me kind of walk you through it a little bit, but I'm not going to give you the answer until I give you a chance to try it yourself. When you type this into your calculator, try to make it as easy as possible. Now, even though I have parentheses here, and I kind of mentioned using them in the previous slide, you really don't need to do that. Your calculator understands the order of operation, and take advantage of that. The way that you would type this into your calculator is really quite easy, and you should only have to hit the equal sign once. What you don't want to do is do one calculation, write down an answer, and then another calculation, write down an answer, and then another calculation, write down an answer, and then add those three together. Better than even chance you're going to be making a mistake with all of those numbers, all of those calculations, and rewriting them down again and typing them back into your calculator again. Do it as follows. So you with me? Have your calculator out. Follow my lead. Type in 0.7870 times 23.99, just that, don't do anything else, plus 0.1013 times 24.99 plus 0.1117 times 25.94. Then hit the equal sign, and you should get 24.31. Now, if you're not getting that, please pause the video and go back and retype this into your calculator. Again, just take this number times this, plus this number times this, plus this number times this. Do not hit the equal sign anywhere along the line. Just multiply, plus, multiply, plus, multiply. It's not uncommon at all for me to see the calculation, the work set up perfect, and the wrong answer. And while I'm mentioning that, as you'll always see, but just to kind of reiterate, you always must show your work. And in my classroom at school, above the whiteboard, I have a sign that says you must show all work with correct units and sig figs. The units are here, and sig figs would be the number of decimal places here. Notice that the atomic mass is to 2 decimal places, and so we would want to report our average atomic mass to the same accuracy. So, answer to the question, do you need to show work? The answer is yes. Answer to the question, do I always need to show work? The answer is yes. All right. Okay, we'll be doing more of this practice later on, but for now, oh, I'm sorry, I forgot to point out to you. We can double check that answer. That answer is the very atomic mass that you would find on your periodic table. So anytime that I give you the atomic mass of an actual element, not a pretend element, you should be able to double check on the periodic table that your answer is what you find there. Now, it might be like slightly different. It might be like 24.30 or something like that. But if you did a calculation for magnesium and you came up with, say, 22.95, well, no, that's clearly not the atomic mass. Okay, so that is it for now. End of notes.